In this lesson, you will learn about the formal definition of a limit and delta-epsilon proofs. First up, we need to do an algebra review of inequalities on a number line involving absolute value. In this example, we have to write each solution as a single inequality involving absolute value. Let's take a look at this first diagram where the variable is x. Now, if you're not familiar with this variable right here, that symbol means delta. So in this diagram, we have an x value of c, and we go out to the right to c plus delta, and back to the left to c minus delta. That tells us that the distance here is delta, the distance here is delta. So if our variable is x, and x can be anywhere on this interval, we know that the distance between our x variable and c would have to be less than delta. So the way we would say this inequality is the absolute value of x minus c has to be less than delta. Remember that absolute value of a difference gives us the distance between those 2 points, so we are saying the distance between x and c has to be less than delta. Now we knew that it was less than and not less than or equal to because of the curved brackets here. And you want to make sure that you understand if we had an x value, say over here, then the distance from that x value to c would be greater than delta. Or if we had an x value over here, then the distance from that x value to c would be greater than delta. So if we want to keep our x values in this region, then we have to make sure that the absolute value of x minus c is less than delta. Here we may have another new variable for you. This variable right here is called epsilon. I want you to pause the video, try this next one on your own, then restart when you're ready to check your answer. Here we have a vertical number line with a point L on that number line. We can go up to a maximum of L plus epsilon or down to a minimum of L minus epsilon. That tells us that the distance from here to here is epsilon, and the distance from here to here is also epsilon. So if our variable is f of x, and we want f of x to stay inside this interval, then the distance between f of x and L, which is given by the absolute value of f of x minus L, must be less than epsilon. Next up, we have the formal definition of limit. And everything in this entire section has been leading up to this definition, which is the single most important definition in the entire section. Let f be a function defined on an open interval containing c. Let L be a real number and x is not equal to c. Then the limit as x approaches c of f of x equals L means the following. For any given epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Now I know this is a big definition and it can feel a little bit intimidating, so let me help you understand the pieces here. To say that f is a function defined on an open interval containing c, that just means if we are on this delta interval around c, that every x value in that interval has a corresponding y value that does exist. So to say that f is defined on the interval means that nowhere on the interval is f undefined. Every x has a y value. Now L is a real number. We see that it's on the vertical axis here, so L is a y value. X does not equal c, so that means our x value is near c, but it doesn't equal c. We're told that we will be given an epsilon greater than 0, and epsilon is a distance, so by definition it must be positive. Delta is also greater than 0, and again, it is also a distance, and so by definition must be positive. To say that the absolute value of f of x minus L has to be less than epsilon is talking about this interval here. And this inequality, the absolute value of x minus c less than delta, is talking about this interval down here. Now let's zoom in on this diagram and understand in more detail what's going on. Now to say that we have the absolute value of f of x minus L is less than epsilon means that our y values will have to stay inside this region. Our y values have to all be within a distance of epsilon from L, the limit value. If we drop down and take a look at the x values associated with those y values, if we were to let delta run all the way to the left side, we have to then have a matching delta of the same size going out to the right side. Now, if we let that happen, notice that that x value would result in a y value that ends up being outside our allowed region from L minus epsilon to L plus epsilon. So then what we would do is we would actually use the right side here. We would say that delta can go out this far to the right and remain inside our epsilon region. Then that means we can go to the left by that same amount. So now if we have the absolute value of x minus c is less than delta, and we let our x values live in that region, then we are guaranteed that our y values will all stay within epsilon of L. Now notice down here on the lower end, our y values don't go all the way down to L minus epsilon, and that's okay. All we are required to do is make sure that our y values never get outside of the epsilon interval. It's okay if the y values get clamped down even more. We just have to guarantee that every y value that results from our delta interval will be inside our epsilon interval. Let's take a look at a little bit different function. Here's our graph of f of x. Remember that epsilon will control the distance between the y value of our function and the limit value L. So that's going to be on the vertical axis here. We have to find a delta to control the distance that our x value is allowed to be from C. So that will be on the horizontal axis here. Now, as epsilon gets bigger, we can see that delta has to change as well. So if we want to keep our y values within the zone from L plus epsilon down to L minus epsilon, then we will need to keep our x values within delta of C, meaning our x values can go to C minus delta up to C plus delta. Now, if we let epsilon get bigger, then delta has to get bigger. Now, in this case, notice that it's the region to the left of C that controls how big delta can get. Because if we allow delta to go all the way out to the right here, that means we have to go the same distance to the left here, and that x value would result in a y value that's over here, which is outside of our given epsilon region. Now, it's important to notice that keeping our x values within delta of C will actually result in our y values staying in the region bounded by this dotted line here and the lower limit of L minus epsilon. And that's okay. Remember, the requirement is that our y values have to stay within epsilon of L. So if the y value is clamped down even further up here, that's just fine. That does not violate the requirement that the y values are within epsilon of L. So for any given epsilon, we have to find a delta that will keep our y values in this region. And as epsilon changes, delta will change to match. And there will also be functions where when we work back from the epsilon interval, it immediately turns into a delta interval that's already symmetric, exactly the same size on both sides, and keeping our x values within delta of C will keep all of our y values within epsilon of L. Next, you will learn how to find delta for a given epsilon by applying the formal definition of a limit. In this example, given limit as x approaches 5 of the quantity 2x minus 3 equals 7, find delta such that if the absolute value of x minus 5 is less than delta, then the absolute value of the quantity 2x minus 3 minus 7 will be less than 0.01. Let's bring up the formal definition of limit. Now, looking at the limit here, we see that 5 is acting like C. So the C is there and there. 2x minus 3 is our f of x. So that means over here, we're taking the absolute value of f of x minus. Now the 7 is L, the limit value. So over here, 7 is L. And we know that the absolute value of f of x minus L has to be less than epsilon. So that tells us that epsilon is 0.01. And now, of course, this is the absolute value of x minus c less than delta. So now you can see the pieces of the definition. Now, if we translate this to our diagram here, we know that epsilon is 0.01. So that means if we go up and down by epsilon, which is 0.01 in either direction, then that means this y value right here is 7.01. This y value here is 6.99. And what we have to do is find delta, which will be the interval around our value of c, which of course is 5. Let's draw this in here. We know that delta has to go this way and this way. And our job is to figure out how close do we have to keep our x values to 5 so that our y values will be within 0.01 of 7. And just to be clear, this interval here on the y-axis is the absolute value of the quantity 2x minus 3 minus 7 being less than 0.01, and this interval here on the x-axis is the absolute value of x minus 5 being less than delta. So let's start off with our f of x minus L statement here. So we have absolute value of 2x minus 3 subtract 7. Now, if we simplify that, we see that that would equal the absolute value of 2x minus 10. Now, this can be factored. We can take out the absolute value of 2 and take that times the absolute value of x minus 5. We know that the absolute value of 2 is 2. That has to multiply the absolute value of x minus 5. Now, one thing we know is that the absolute value of x minus 5 is going to be less than delta. It doesn't equal delta, but it is less than delta. So this quantity would not equal 2 times delta. This quantity would be less than 2 times delta if we make that substitution. Because we know that absolute value of x minus 5 is less than delta, then we are able to change this equality to an inequality of less than, and 2 times absolute value of x minus 5 becomes less than 2 delta. Now, if we could just pick what delta is, we don't know what it is, so I'm going to leave an open set of parentheses here. I don't know what delta is at this point, but I know that I want this quantity, which is right here, to work out to be less than 0.01. So what this does is this helps us figure out what delta needs to be, because 2 times whatever we put in for delta has to work out to be 0.01. So 2 times delta, let's let that be 0.01, then delta is going to equal 0.01 divided by 2, which is 0.005. So at this point right here, if we were to put in 0.005 for delta, then we would be guaranteed that the absolute value of quantity 2x minus 3 minus 7 will work out to be less than 0.01. So because that algebra worked out, we would choose delta to be 0.005. Now, it's important to understand that this absolute value of quantity 2x minus 3 minus 7 really appears in every step here. But if you show your work vertically like I have here, then I will allow you to write it once up here, and then it will be implied going down, and just show all of your work lined up here on the right hand side with your equal signs and your less than signs all lined up. If you do that, then you can just write this f of x minus L statement one time. Now you will learn how to do a delta-epsilon proof. Here, we have to prove that the limit as x approaches 2 of the quantity 4x minus 3 is equal to 5. Every delta-epsilon proof is based on the formal definition of limit. So let's bring that up. And we see in this limit, x is approaching 2. So remember that that is c. So c is 2. This 4x minus 3 is f of x. And 5 is L. Now in the definition, it says for any given epsilon greater than 0, there exists a delta greater than 0. So when we write our proof, we have to say, given epsilon greater than 0, choose delta equals, in this case, for this proof, it works out to be epsilon over 4. This value will be different in every proof, but the format of beginning your proof with given epsilon greater than 0, choose delta equals whatever, will be the first line of every delta-epsilon proof that you write. Now let's go back to the definition. It says, if the absolute value of x minus c is less than delta, now remember in our case, c is 2, so we will write, then for the absolute value of x minus 2 less than delta, we get. So this will be the first line of every proof that you write, except that your delta will change from proof to proof, and your value of c will change from proof to proof. Now referring back to the definition, we have to prove that the absolute value of f of x minus L works out to be less than epsilon. So in our case, the absolute value of f of x minus L is going to be the absolute value of the quantity 4x minus 3 minus 5. Now what we have to do is some simplifying and substitutions, and ultimately we have to show that that works out to be less than epsilon. So let's get started. First, we can do a little bit of Algebra 1 and rewrite this as the absolute value of the quantity 4x minus 8. We can factor out an absolute value of 4 and multiply that times the absolute value of the quantity x minus 2. We know that the absolute value of 4 is 4, and then we still have absolute value of quantity x minus 2. Now we know that absolute value of quantity x minus 2 is less than delta, so then this quantity is going to be less than 4 delta. Now we know ultimately we need the absolute value of f of x minus L to work out to be less than epsilon. So what we want to do is figure out 4 times what quantity would work out to be less than epsilon. And it's pretty easy to see that at this point we would choose delta to be epsilon over 4. That's why we chose it, so that when we take 4 times epsilon over 4, we end up with epsilon. And remember, if you write your work vertically, lining up the equal signs and the less than signs, then I will allow you to write this left-hand side just one time. Now, because we were able to prove that given any epsilon, we can find a way to make f of x minus L become less than epsilon by choosing delta to be epsilon over 4. So therefore, the limit as x approaches 2 of the quantity 4x minus 3 is equal to 5. In this example, we have to prove the limit using a delta-epsilon proof. We are given the limit as x approaches 6 of the quantity 3/2 x minus 2 is equal to 7. Now, every single delta-epsilon proof that you write will begin with the same first line. So here we go, proof. You are allowed to abbreviate the word proof with PF if you like. Given epsilon greater than 0, choose delta equals. Now at this point, we don't actually know what delta is going to equal. So we'll leave that blank right here for just a couple of minutes. But you must have given epsilon greater than 0, comma, choose delta equals. Now to finish that first line, we have to say, then for, remember it's quantity absolute value of x minus c. And in this case, c is equal to 6 less than delta, comma, we get. Now we have to look at proving that the absolute value of f of x minus L can be worked out to be less than epsilon. We have absolute value of f of x, which is 3 over 2x minus 2, and we have to subtract L, which is 7, and we want to show that that will work out to be less than epsilon. So let's do some algebra to simplify this. We get that this is equal to the absolute value of 3 over 2x minus 9. Now we can factor out an absolute value of 3 over 2. So then think of multiplying each term on the inside by 2 over 3. If we multiply this by 2 over 3, it cancels out and we just get x. If we multiply this 9 by 2 over 3, then we get 6. Always double check your factoring. 3 over 2 times x gives us 3 over 2x. 3 over 2 times 6 will give us 9. Now we know that the absolute value of 3 over 2 is 3 over 2, and we still have absolute value x minus 6. And now this is the mathemagic portion of every delta-epsilon proof. You will always end up with a factor that is your absolute value of x minus c term. It will work out 100% of the time that you get this factor somewhere. We know that absolute value of x minus 6 has to be less than delta, so then this quantity has to be less than 3 over 2 times delta. Now we know that we're going to have to choose a delta, so let's write less than 3 over 2 and then make a blank set of parentheses where we will figure out what delta is going to be so that this will end up being less than epsilon. So you can see we need 3 over 2 times something to equal epsilon. So if at this point we choose delta to be 2 over 3 epsilon, if I substitute that in here, you can see the 3's will cancel out, the 2's will cancel out, and we are left with epsilon. So, given any epsilon greater than 0, if we choose delta to equal 2/3 of that epsilon, then it will always work out that the absolute value of 3 over 2x minus 2 minus 7 will always work out to be less than epsilon. And because we were able to show that, we say therefore the limit as x approaches 6 of 3 over 2x minus 2 is equal to 7. And just a reminder, if you keep all of your equal signs and less than signs lined up, I will allow you to write this left-hand side just one time. In this example, we have to prove the limit using a delta-epsilon proof. We are given that the limit as x approaches 4 of the quantity 3 minus 1/2 x is equal to 1. Every delta-epsilon proof that you write will begin the same way. So we say proof given epsilon greater than 0, choose delta equals, now remember we don't know what it is, so we will leave that blank just momentarily. Then for absolute value of x minus 4, because our value of c is 4, less than delta, comma, we get. Now we have to look at the absolute value of f of x minus L, so that would be our f of x, which is 3 minus 1/2 x minus L, which is 1. Now let's do a little algebra and simplify this expression. We get absolute value of negative 1/2 x plus 2. We can factor out the coefficient of the x term, so absolute value of negative 1/2 times the absolute value of x minus 4. Always double check your factoring. Negative 1/2 times x is negative 1/2 x. Negative 1/2 times negative 4 is positive 2. We know that the absolute value of negative 1/2 is positive 1/2. We still have absolute value of x minus 4. And now here's the mathemagic again. We got the factor of absolute value of x minus 4, which it will always work out, we get that, and we see that that is less than delta. So then that means this quantity will be less than 1/2 times delta. Now what we want to do is figure out what delta needs to be so that when I take 1/2 times whatever I pick for delta, it will end up being less than epsilon. So at this point is where we can choose delta to equal 2 times epsilon, because we see if we put that in here, 2 times epsilon, then the 1/2 times 2 cancels out, and we are left with epsilon. So here, once we make this choice, we can go back to our first sentence. Given epsilon greater than 0, choose delta equals 2 epsilon. If we do that, then for the absolute value of x minus 4 less than delta, we get that our f of x minus L works out to be less than epsilon. Therefore, we just proved that the limit as x approaches 4 of 3 minus 1/2 x is equal to 1. In this example, we have to prove the limit using a delta-epsilon proof, given that the limit as x approaches -1 of the quantity 6x plus 9 is equal to 3. So I want you to pause the video and write the whole entire first sentence on your own, and then restart the video when you're ready to check that first sentence. So we have proof given epsilon greater than 0, choose delta equals, we don't know yet, so we'll leave that blank. Then for absolute value of x minus c, which is -1, and of course that equals absolute value x plus 1, and we know that will be less than delta, comma, we get. So double check your first step there. Make sure that you have given epsilon greater than 0, choose delta equals, and you've left that blank for now. Then for absolute value of x minus -1, or if you didn't choose to write it this way and you went immediately to this form, that's fine too. But we have absolute value of x plus 1 less than delta, we get. Okay, now that you've got the setup going, pause the video and try writing the rest of the proof, then restart the video when you're all done and you're ready to check. We have to do the absolute value of f of x minus L, so that would be the quantity 6x plus 9 minus 3. Now we're going to simplify that. We would get absolute value of 6x plus 6. We can factor out the coefficient of the x term, so factor out absolute value of 6, and you would take that times absolute value of x plus 1, we know that the absolute value of 6 is 6, and we're multiplying that times the absolute value of x plus 1. Now we know that absolute value of x plus 1 is going to be less than delta, so this expression will be less than 6 times delta. We know that we'll need to figure out what delta is going to be, so that when we take 6 times whatever we choose for delta, we end up with less than epsilon. So at this point, we would choose delta to equal epsilon over 6, because if we choose that, epsilon over 6 times 6, of course, they cancel, and we get epsilon. Now you have to always go back to that first statement. Given epsilon greater than 0, choose delta equal to epsilon over 6, then it will work out that our f of x minus L becomes less than epsilon. So therefore, the limit as x approaches -1 of 6x plus 9 is equal to 3. Here we do a quick algebra review. This function here, min, stands for the word minimum. And the minimum of a list of values outputs the smallest, meaning the minimum value in the list. And we're going to need that to do our next couple of proofs. In this example, we have to prove the limit using a Delta-Epsilon proof. We're given the limit as x approaches 5 of the quantity x squared minus 3x is equal to 10. Now we start off, like all our proofs, with given epsilon greater than 0, choose delta equals, now here's where it's different. We are going to make use of this minimum function here. So delta will be the minimum of the following two numbers, 1, and then whatever it is we come up with for delta later in our proof. We don't know what this is yet, and I'll explain how we're going to use the 1 in just a minute. Then, for absolute value of x minus 5 less than delta, because our value for c is 5, comma, we get. Now we have to look at the absolute value of f of x minus L. So that's the absolute value of the quantity x squared minus 3x minus L, which is 10. So this is equal to the absolute value of x squared minus 3x minus 10. Now we recognize that this quadratic is a trinomial that can be factored, so we will get the absolute value of x plus 2 times the absolute value of x minus 5. Remember to always double check your factoring. X times x gives us the x squared. We get 2x from the inside terms and minus 5x from the outside terms, which would combine to be negative 3x, and then last times last, we get negative 10. Now here, notice we don't have any constant terms. We have this absolute value of x plus 2, which we have no idea what that's going to be, and we have the absolute value of x minus 5, which we definitely know is going to be less than delta. So then we can say that this expression will be less than the absolute value of x plus 2 times delta. Now, before we can figure out what delta is going to be, we have to take a look at this factor here of absolute value of x plus 2. And that's where this minimum function is going to help us. Let's go off on the side and make a little number line here. We know that our x value is approaching 5, so let's put 5 on our number line. Now we know that the interval around x means we could go delta in this direction or delta in this direction. We don't know what delta is, but we know that it's actually going to be a tiny number when we're doing limits. Remember, the limit is about x approaching 5, so that means x is getting infinitely close to 5 from the right or infinitely close to 5 from the left. But what we need to do here is some worst case scenario analysis. So we're going to say, what happens if we let delta be absolutely ridiculously gigantic, which would be 1. So in terms of limits, 1 as a distance is a huge distance because we're talking about being infinitesimally close to 5 from the right or left. So if we let delta equal 1, which is ridiculously huge, then that means our x value could be as small as 4 or as large as 6. Now what we are going to do is analyze what could happen to the absolute value of x plus 2 under these two extreme conditions where we let delta be ridiculously large. Now, if x were to get as small as 4, then the absolute value of x plus 2 becomes the absolute value of 4 plus 2, which of course is the absolute value of 6, which is 6. If we let delta equal 1 going to the right, our x value could get as big as 6, and then the absolute value of x plus 2 would be equal to the absolute value of 6 plus 2, which is 8, and the absolute value of 8 is 8. Whichever one of these numbers is bigger is the worst case scenario. So what we do is we say that this expression, absolute value of x plus 2, at its worst, could be as big as 8. And then what we want to do is pick delta so that when we take whatever we pick for delta times 8, we end up getting less than epsilon. So at this point, we would choose for delta to be epsilon over 8. Now if we plug that in here, epsilon over 8 times 8, those cancel, and we're left with epsilon. So we can come up here to our first sentence, given epsilon greater than 0, we will choose delta to be the minimum of the following two numbers, 1 and epsilon over 8. Whichever of those two numbers is smaller, that's the one we're going to use for delta. Now, virtually all of the time, the epsilon over 8 will work out to be the smaller one. We only used this value of 1 to help us come up with a worst case scenario. The choice of 1 is arbitrary. We could have picked 1,000, or we could have picked 2, or we could have picked 27. But since 1 is so gigantically huge compared to delta being infinitesimally close to our value of c, 1 is plenty big and it's an easy number to work with, so we choose to use it. Now, since our f of x minus L worked out to be less than epsilon, we can say, therefore, the limit as x approaches 5 of x squared minus 3x is equal to 10. In this example, we have to prove the limit using a delta-epsilon proof. Given limit as x approaches -2 of the quantity x squared minus 2x minus 3 is equal to 5. Pause the video, try this one on your own, then restart when you are ready to check your answer. As always, we start with our first statement of the proof. Given epsilon greater than 0, choose delta equals. Now, because our f of x is a quadratic, that is your signal that you will need to use the minimum function. And we always take the minimum of 1 and some expression for delta that we don't know what it is yet, so we will leave that blank. Then, we have to do the absolute value of x minus c. Our value of c is -2, so we have absolute value of x minus -2, which of course becomes the absolute value of x plus 2, and that will be less than delta. We get. Now check everything in your first statement. Do you have every single one of these elements going? The only thing you could skip having would be if you wrote the delta statement right off as absolute value of x plus 2 instead of showing this. I like to show this because it reinforces that we're doing x minus c, and then I simplify it. But it's okay if you go right to this statement. Now we have to look at absolute value of f of x minus L. So we have absolute value of x squared minus 2x minus 3. That's our f of x. We have to subtract L, which is equal to 5. Now let's simplify. This becomes the absolute value of x squared minus 2x minus 8. We can factor this into the absolute value of x minus 4 times the absolute value of x plus 2. Now always double check your factoring. X times x gives us the x squared. Negative 4x plus 2x gives us negative 2x. and negative 4 times positive 2 gives us negative 8. We don't know what's going to control this factor, but this absolute value of x plus 2 we know is going to be less than delta. So then we can say that this expression is less than the absolute value of x minus 4 times delta. Now we need to control this factor, and that's where we do our worst case scenario analysis. Let's make a number line. We know that our x value is approaching negative 2, so that's what will go on our number line. We know that delta will go off to the right, and delta will go off to the left. And in our worst case scenario analysis, we are going to let delta be as gigantic as 1. If that happens, if we're at negative 2 and delta is 1 going to the left, then that means we are over here at negative 3. If we start at negative 2 and go to the right by 1, then we are at negative 1. Now let's analyze what happens to this factor of absolute value of x minus 4. If we take negative 3 and plug it in for x, then we have the absolute value of negative 3 minus 4, which of course is the absolute value of negative 7, which is 7. Whereas if we take the absolute value of x minus 4 and we plug in negative 1, that becomes the absolute value of negative 1 minus 4, which is the absolute value of negative 5, which is 5. Remember that in our worst case scenario analysis, the bigger number is always the worst case. So that means 7 is the worst case here. Taking our worst case scenario and substituting in, this expression becomes less than 7 delta. So now we know we have to pick an expression for delta so that when I take 7 times that expression, it's going to end up being less than epsilon. And at this point is where we would choose delta to be epsilon over 7. Because when we substitute that in for delta, epsilon over 7 times 7 becomes epsilon. So now we go back to our first statement. Given epsilon greater than 0, choose delta to be the minimum of 1 and epsilon over 7. And if we do that, then we know that our f of x minus L statement will end up being less than epsilon. Therefore, the limit as x approaches negative 2 of the quantity x squared minus 2x minus 3 is equal to 5.